Hello everyone, and welcome to the fourth session of this lecture series entitled EXA in Structural Engineering. In the previous session, we defined the first four equations in the table shown on screen, and today we will continue explaining the rest of the equations to be inserted into our Excel template to calculate all of the required output parameters. For the fifth equation, yt, which is defined as the distance from the extreme fiber in tension to the centroid of the second layer of steel, and referring to the figure shown on screen, this distance is the summation of concrete cover, diameter of stirrup, diameter of bar in the layer farthest from the neutral axis, then the vertical distance between layers of reinforcement, and half the diameter of bar in the second layer. The vertical distance between two layers of reinforcement shall not be smaller than 25 millimeters. Where the ACI code stipulates that the reinforcement in the upper layer shall be placed directly above reinforcement in the bottom layer with a clear spacing between layers of at least 25 millimeters. Therefore, if we go back to this equation here, we can see that there is a 25 millimeter distance embedded in the equation of yt. Now, if in your work you know that this distance, 25 millimeters, will not be constant, the vertical distance between layers of reinforcement will change from one problem to the other, then you can define the vertical distance between layers of reinforcement as an input parameter and use that to calculate your output parameters. We can now define y bar, which is the distance to the centroid of the entire area of steel reinforcement measured from the extreme fiber in tension. It is nothing but the equation of centroid that we learned in statics, where y bar is equal to the summation of A times y divided over the summation of A. Next, we define the effective depth D as the total depth of the cross-section minus y bar, which is different from dt, defined as the distance from the extreme compressive fiber to the centroid of the layer farthest from the neutral axis, and here defined as h minus yb. The reinforcement ratio is the total area of steel reinforcement calculated previously here, divided over the effective area of concrete, which is B times D. The minimum width of the cross-section is defined as the width required to encompass the number of bars in the layer farthest from the neutral axis, because we know that the layer farthest from the neutral axis will have the largest number of bars when compared to the second layer in order to have an efficient layout of steel reinforcement. The concentration of steel should be placed in the layer farthest from the neutral axis. I have an equation ready for the minimum width of the cross-section. I'm going to paste it here, which reads B minimum is equal to 2 times the cover plus 2 times the diameter of stirrups. Then we need to include the total number of bars in that layer multiplied by the diameter of bars in that layer, as well as the number of spacings between these bars multiplied by the actual spacing between these bars. You should note that in a layer of steel reinforcement, the number of spacings will always be equal to the number of bars in that layer minus 1. So if we have 4 bars in one layer, we will have 3 spacings between these 4 bars. If we have 6 bars in one layer, then we will have 5 spacings between these 6 bars in that particular layer, and so on. Another thing that you need to pay attention to is the clear spacing between bars defined by the ACI code as 25 millimeters or the diameter of bar, whichever is greater. And therefore, if we look at the syntax used here in Excel, we are saying that B minimum is nothing than 2 times the cover plus 2 times the diameter of stirrups plus the number of bars in the layer multiplied by the diameter of bars in that layer plus the maximum between 25 millimeters and the diameter of bar, the maximum between these two multiplied by the number of spacings in that layer. Max in this equation is an abbreviation for maximum. So if you have two values, Excel will choose the larger between them. This here is the number of spacings, as the number of spacings is equal to the number of bars in a single layer minus 1. But each of these spacings is equal to the diameter of bar, or 25 millimeters, whichever is greater. If we look now at AS minimum, we will see that AS minimum according to the ACI code has two values. Eventually you will have to pick the largest between the two. That's why we are using the maximum function here again. The first value is shown here, separated from the second value by a comma. If we go now to the correlation coefficient beta 1, the value of beta 1 has three scenarios depending on three conditions, and we will have to use an if statement in Excel in order to obtain the required results. An if statement is a very powerful tool in Microsoft Excel that helps you decide which value to use when you have more than one option. The syntax, as can be seen here, is as follows. There is an if followed by the first condition and then the result of the first condition, followed by another if. We call it a nested if statement. So if the first condition is not satisfied, then we are telling Excel to check the second condition. If the second condition is satisfied, then this here is the result of the second condition. Now, there is a third if statement, but it is not mentioned here because it is implicit. If neither the first nor the second conditions are satisfied, then use the third value given here as 0.65, as stated in the equation defining the correlation coefficient of beta 1. Note that beta 1 is dependent on the compressive strength of concrete. So we have the compressive strength of concrete in three zones or three intervals. When the compressive strength of concrete is between the closed interval of 17 and 28 megapascals, then we have a constant value for beta 1, which is 0.85. If f sub c prime is within the open interval of 28 and 55, then we have an equation to calculate the value of beta 1. And if f sub c prime is greater than or equal to 55 megapascals, then again we have a constant value for beta 1, but this time it is 0.65. I cannot emphasize this enough. If statements are very important when you are working in Excel because they facilitate your work and help you organize your conditions and your outcomes. So let's look again at this syntax used in Excel. We have the first if, the second if, and then there is no third if. It is implicitly included through the outcome when the first and second if statements are not satisfied. Let's try to look at this in a simpler way here. We have two if statements. If we want to say it correctly, we should have three if statements for the conditions shown here. We have this first condition with its result, the second condition with its result, and the third condition with its result. But the way the if statement is built up in Excel, you can tell Excel that if the first if statement is not satisfied and the second if statement is not satisfied, then directly go to the result of the third implicit if statement, which is if f sub c prime is greater than 55 megapascals. Because you can check here that the first condition specifies that f sub c prime should be greater than or equal to 17 and it should be less than or equal to 28, which is the first condition here. So if this condition is satisfied, the result should be beta 1 is equal to 0.85. In the second if statement, if f sub c prime is greater without the equal sign than 28 and smaller, look here, without the equal sign to 55, then the second condition is satisfied. If the second condition is satisfied, then this here is the outcome, which is written here because I couldn't fit it on one line. So the result for the second if statement is this one here, which is the equation for the second condition. Now, if the first condition is not satisfied and the second condition is not satisfied, then implicitly we are in the third condition. Therefore, in such a scenario, the value for beta 1 should be 0.65, which is directly stated here. The next output parameter that we should look at is A, which is the depth of the Whitney rectangular stress distribution. Any civil engineer should truly understand the correlation between A, which is the depth of the Whitney rectangular stress distribution, and C, which is the depth to the neutral axis, and understand how these two are related to each other through the beta 1 coefficient. A is nothing but the total area of steel reinforcement multiplied by the yield stress divided over 0.85 f sub c prime times B. This is written in Excel syntax simply in this form. You have AS times Fy. The product is then divided over the product of 0.85 f sub c prime and B. The depth to the neutral axis C is defined as A, which is the depth of the Whitney rectangular stress distribution, divided over beta 1. I would like to remind you here that we couldn't use the name C for our output variable, as C is reserved in Excel and cannot be used as a name whether in small letter or capital letter because it is reserved for column, and thus we have assigned the name C of A to our output variable C. Therefore, whenever C is going to be used in my equations after this point, the name assigned to the output variable C, which is C of A, will be used instead. Let's call it a day for session number 4, and we will continue in session number 5. Best wishes.